Bismillahirrahmanirrahim. We will start today chapter 6, Work and Energy. شغل والطاقة. Chapter contents, we will speak about work and energy, conservation of energy and power. At the beginning, work. While most people feel that work is done when you work on a problem, like solving an equation, or do homework, physicists say work has only been done when a force is applied to an object and the object moves in the direction of the applied force. So we have in physics a special meaning for work. When we speak about work, there is force applied and movement, both together, not only force but also movement. Definition of work: force in direction of displacement. Force in the direction of displacement. The equation is so important. Work equal force times distance. WFD. You know that force measured in Newton and the distance measured in meter. Newton meter, we call it joule. Let's do something. You know that force equal MA and M kilogram and acceleration meter per second square, that what we call it Newton. But W equal F D or Fs, force times displacement. So force in Newton means kilogram meter per second square times d, distance or displacement meter. So all of that exactly kilogram instead of meter, meter square over second square. That's what we call it joule. So you have to know that Newton, kilogram meter per second square, and joule, kilogram meter square per second square. I hope you understand that. Well, the figure below illustrates work being done as a force. There is a force here, pushes a box through a displacement. There is a displacement D. The work done equals W equal FD. So there is a force, applied force, a constant force, and it does work equal FD. As you see, the force in the direction of the displacement, and it is important. The dimensions of work are force in newtons times distance in meters. The product of the two Newton meter is called joule, in honor of physicist James Prescott Joule. So up till now you have only one equation, W equal FD. W is measured in joule, force Newton, displacement meter. So a joule represents a relatively modest amount, simple amount of work. Example, you do a joule, 1 joule of work when you lift a medium-sized apple through a height of 1 meter. So the table below provides some examples of typical amounts of work. This is not for memorizing. Don't memorize it. And imagine that a human heartbeat 0.5 joule. Burning 1 gallon of gas, 10.8 joule, and so on. You don't need to memorize it. It may come as a surprise that no work is done while holding a heavy object such as a suitcase. Imagine that you are standing here and holding a suitcase. You are not doing work. By the definition of work equals 0 because the suitcase doesn't move. No work is done. However, you become tired only because your muscles here, your muscle cells are doing work holding the suitcase. But by the definition, the suitcase doesn't move, so no work is done by the suitcase. We have many examples. I'll give you example. Imagine that you are pushing with a force a wall. You are pushing the wall, and the wall doesn't move, so no work is done. Your muscles only tired because the wall is not moving, so there is no work done on the wall. Work is easily calculated when the force and displacement are in the same direction. Like this example, you are pushing a specific box a distance d, you move it to a new place. Okay, so you multiply F times d. But hold on, what if the force is not in the same direction as the displacement? But how is the work calculated when the force is at an angle to the displacement? Like what? Like that. Imagine this is the box and you push it or you pull it with a specific angle here with the horizontal, the direction of the motion. The figure below shows a person pulling a suitcase at an angle theta with respect to the direction of the motion. As you see, there is an angle theta with the direction of the motion. What you will gonna do here, you will resolve the vector force in two directions, horizontal and perpendicular. The one that make work, the one in the same direction as the movement, as the motion, so the only Fx or the component in x direction. The component of force in the direction of the displacement is F cosine. You know well that if you have a specific vector here like force, and you can resolve this one by using, resolving it F cosine theta and F sine theta. The motion in x direction, so you will use this component, and this one doesn't make work. The perpendicular or the normal or the component at right angle to the motion doesn't make any work. Okay, imagine that you come above a car here and stand up and start to push the car down. The car will not move, right? Why? Because this direction is perpendicular to the direction of the motion. So no work done by the force perpendicular to the direction of the motion. So in this case, such as this, only the component of the force in the direction of the displacement does work. So instead of the law that W equal F D, you will use W equal, instead of F cosine theta times D, or we will write it F D cosine theta. Looks better. Notice in the previous figure that the component of force in the direction of the displacement F cosine theta. Therefore, the work equals F D cosine theta as we said above here. So, definition of work. with force and displacement at an angle. Work equals force times the distance times cosine of the angle between the force and displacement. This is a box and moves this way, but the force is this way. So we will get, instead of F cosine theta times the displacement G. So W equal F D cosine theta, and the same unit is Joule. Or don't forget Newton meter. Okay, guys? Let's go to the next slide. As you see, the work can be positive depending on the angle, or negative or zero. Here in the first case, because cosine theta and theta less than 90 and larger than 0, it is positive. Cosine, يعني use the calculator, cosine 30, 40, 50, 60, it is positive amount. So work is positive because FD positive times cosine theta and cosine positive, so work is positive. So work is positive if the force has a component of in the direction of motion like this one. What about if the force is perpendicular? Do you remember? We said cosine theta or cosine 90, cosine 90 equals F. So no work is done when the force is perpendicular, up or down. So work is 0 if the force has no component in the direction of the motion. This is the direction of the motion. And force perpendicular. So it will not cause work because there is no motion by the perpendicular force or the normal force. Like I'll give you example. Imagine this box. This box has weight W, right? And it doesn't move because this weight doesn't do any work. Work may be negative depending on the angle if the force has a component opposite the direction of the motion. If the component of the force opposite to the direction of the motion larger than 90 and less than 270. Use the calculator to get cosine any angle above 90, you will find it negative sign. So work may be positive, negative, or 0. When more than one force acts on an object, imagine that there is more than force. There is force here and force there and force up and force like from many directions. The total work is the sum of the work done by each force separately. We calculate the work done by each force, and after that we get the combination of the work. For example, if F1 do work W1, F2 does work W2, F3 does work W3, and so on. The total work equals W1 plus W2 plus W3. When work is done on an object, the object's energy changes. For example, when you push a shopping cart, your work goes into increasing the cart's kinetic energy. Imagine that there is cart here and you start to push it. Imagine it was moving with a specific velocity, and when you push it with a specific force, its velocity or speed increase. Or it may be at rest, stationary, and when you push it, it has now a speed. So when you push a shopping cart, your work goes into increasing the cart's kinetic energy. When you climb a mountain, your work goes into increasing your potential energy. Thus, kinetic energy is energy of motion. This is a definition of kinetic energy, guys. Kinetic energy is energy of motion. Potential energy is the energy of position or condition. And we will describe each one. Kinetic energy and potential energy. Kinetic energy, energy of motion. Potential energy, energy of due to position or condition. Newton's laws and the equation of motion may be used to drive a relation between work and energy. In the figure below, a box is pushed across an ice skating rink with a force. Ice skating rink to decrease the friction force, guys. Make it zero. It is never be zero, but to make it less. Let's see how this force is changing the box's energy. Okay, guys? Let's do it together. From Newton's second law, you know well that F equal ma, so A equal F over m. Don't forget that. From equations of motion, you know that V final square equals V initial square plus 2AD or S, whatever. So we can write it 2AD equal V final square minus V initial square. Let's use A here. So 2 times F over M D equals F V final square minus V initial square. Agree about that? Let's multiply it M over 2. So here it equals FD equal half MV final square minus half MV initial square. FD equals what? Equal work. So W equal half MV final square minus half MV initial square. So this is work, and this is the change in kinetic energy, because this amount half mv square, that we call it kinetic energy. And don't worry, all types of energy and also work is measured in joules. I'll prove that for you. M in kilogram and V meter per second, and you have a square, so kilogram meter square per second square. Do you remember? Kilogram meter per second square times meter. This is Newton and this is meter, and that's what we call it joule, like the work equal FD Newton meter, we call it joule. So we are doing well. So the work done, it changes the kinetic energy, final kinetic energy, minus initial kinetic energy, or half mv final square minus half mv initial square. This is the law or the work energy theory. Let's go back to our PDF. This is the proof, and as you see from the relation, W equal half mv final square minus half m initial square, v initial square, we see that the work done on the box or any other object is related to the quantity half mv square. This quantity is defined as the kinetic energy, or Ke, of an object of mass m and speed v. So kinetic energy half the mass times velocity square. Kinetic energy equal half mv square and kilogram meter per second square, meter square per second square, or what we call it joule. Okay, guys, in general, the kinetic energy of an object is energy due to motion. Kinetic energy is measured with joule, the same unit used to measure work. Got it? The following table provides some examples of typical kinetic energy. So, yeah, it's not for memorizing. Let's see this problem. The kinetic energy increase linearly with the mass and the square of the velocity, because Ke equal half mv square. By increasing the mass, kinetic energy increase. By increasing the velocity, also kinetic energy increase. But hold on, there is square here. You will figure out something now. Imagine a truck 3,900 kilogram moving with speed. What is the kinetic energy? So it is easy. Kinetic energy half mass times the velocity square. You will get this number in joule. B. What is the truck kinetic energy? What is the truck kinetic energy if the speed is doubled to 12 meters per second instead of 6? It is doubled. Hold on, because of the square here, KE equal half mv square. When you double the velocity, the kinetic energy become 4 times. So kinetic energy depends on the speed squared. Therefore, doubling the speed quadrupled the kinetic energy. Try to do it mathematically. Instead of this way, just use the V12 and make it square times the mass times half. You will get the same number. So put in your mind, doubling the speed quadrupled the kinetic energy. And we have a lot of problems here, depending on that in exam view. As the equation W equal half mv square final v square minus half m initial v square indicate the total work done on an object equals the change in its kinetic energy. For you, when you push something, but we neglect the friction, guys, this connection is known as work energy theorem. Total work, W, change in kinetic energy, W equal change in kinetic energy half mv final square minus half mv initial square. Let's see another problem. How much work is required? You have the mass, splinter to accelerate from rest, so V initial equals 0, to a speed V final. So just use the number half mv final square minus half mv initial square, and it is equal 0 because the object was at rest, or the splinter was at rest. So you will get the total work. As we said, the work may be negative, positive, or 0. The sign of the work is related to the change in kinetic energy. If the total work is positive, then the kinetic energy increase. If the total work is negative, then the kinetic energy decrease, like the force of brakes that try to stop the car. If the total work is 0, then there is no change in kinetic energy, right? Okay, guys, that's enough for today. Let's complete the next videos. God bless all of you guys. Assalamu alaikum.